Hello everyone, welcome back to the second part of the practical lecture 4.2, Practical Introduction to OpenFoam. In second part of this lecture, we will have example for multi-phase flow, and we will use OpenFoam to solve and simulate this CFD problem, and we will see how the parallel computing here is accelerating the solution, and we can make the simulation with shorter time. About the problem, it's for multi-phase flow. The condition is transit and non-isothermal. It's using volume of the fluid method, base of the interface capture method. The domain of the problem, as you can see here, we have two fluid, air and water. Each one has a 1 bar pressure, and there is a volume inside the water, which is a sphere. It has a 10 bar. So it's similar to exploding. We want to use the CFD to simulate the condition of the problem and what's happening. To do this simulation, we will use the OpenFoam, and we will see what setup we need to in the dictionary and what command we need to use. And we will look at the parallel decomposition also. Firstly, we will look at the dictionary on the local computer, and then we will see how we can create a batch file and submit the batch file to the HPC cluster and use the capability of the high performance computing. Here we have these directories for the depth charge 2D simple. Going to the CD system. So we are opening the decompose project. Here we can see the setup on the simple one, and the subdomain is expected to be 4. So here the X is 2 and Y is 2. And we will see how we'll create this subdomain. We don't change this setup. We'll keep it the same, and we'll run it. First, we need to create a mesh. Mesh, it's the command here. The mesh is created, and then set fields. This is done. And now we can do the decompose part. Here you see from this parallel decomposition, 4 processors, as we expected to have 4 subdomain here, processor 0, processor 1, processor 2, processor 3, and processor they are 4 from 0 to 3. And we can see number of the cell or mesh in each one. The phase shared with the processor 80, phase shared with processor 2, 40, because the processor 0 has an interface with processor 1 and 2. Each one has an interface with each other, and the number of the interfaces mentioned here. They shared with each processor. So this information here, and now we can visualize these subdomain. Let's keep going on this. So we need to cd is 0, 1, 2, okay. Okay, this created. Processor 1. Processor 2. Now we need to go to processor 3. So if we had 4%, and for all of them we make visualization, now we can go to our view and have a look on the structure of this simple method, how it created the visualization of this processor. Anything here? So we have the simple one. We have processor 0. Now the next one. This subdomain, and 3 of this subdomain. Let's go to the fourth one. So here we have this fourth of them. We can change the color and we can see how they look like. So we can see simple method with the setup for the coefficient. We made it 2 in x and 2 in y. It's same to this. Now we can type the another category to see when we change the coefficient, how it look like. Let's go back to our setup here. So we can close the power view here in this section and we go back here. And remove this processor and we create again new So we see the processor as removed. We can make a new setup the a simple method. When we go here, we can see the method is simple. The domain are 4. We keep this domain 4, but we change the number here to see when we are changing how it look like. And we make this one 4. Let's do the setup. It's saved. So again, we repeat our process to create the mesh and the processor lock mesh. And decompose. Okay, we need to go back through this here. So we on the mesh again. We were in the wrong directory, so we meshes here, and then set field, and then the decompose part. And here we see again the number of the meshes is same to the previous one, but the number of the face shaded processor is different. Each subdomain has a share face only with 1 to the processor number 0 and processor number 3. They have only 1 face shared, but number 1 and 2 they have 2 shared face. Let's look on this subdomain, and we will see what the difference between the previous setup of the simple method. We need to go to enter the processors 0 and make the visualization. And we repeat it for the other 3 processors. This is number 3. So we should have all of them now. So here we can compare it here. And we load the visualization to see how it's working. This is a number 1. Number 0 is content of 0. So from here we can see there is a change between the setup of the domain, the subdomain. Sometimes depend on the geometry of the problem. It's very important to decide where we can have shared faces. So that's why it's important to use which method and how we can use it. There is a fourth subdomain. So we have all subdomain. We can change the color to see how they are next to each other. Completely, they are in difference uh, presentation, how they look like, and as you said, if this one is the first one, and this one is the person number 0, and this one number 3. As you remember here in the number of the shared faces, number 0 and number 3, they have only one. So only one shared face, and these two in the middle, they have two side shared face. So this is the reason, because they have different shared face. So this is showing us when we're using different method of the decomposition, how it's decompose the subdomain, and we are using MPI to solve this kind of a problem. Now, so far we saw how we decompose the domain of the problem. Now we can go to solve a problem with the whole method. Firstly, we run the problem on the local system. Again, we can remove the processor because we don't need them in this part. You can see we don't have the processor anymore. So without parallelization, without power decompose, first time we run code, and then we will run it with uh, decompose processing, and we will see what the difference. So again, we keep the setup of the problem, the boundary condition, the initial condition, the properties same, just running to create the meshes and then solve the problem. First, we start with block mesh. Let's see. And here the field is created. We don't need to use the decomposition. We want to only solve this domain with one person. So we'll see how long time will take for this one, and also how the process. This problem, part of the compressible interform, is depend of the problem. We should use a specific command. Okay, and now we see the running to solve this problem. This will take time. During this progress, we can go to our HPC cluster area, and we see how we can process the in the same method with submitting a batch. Let's open the terminal. LDR system. So we are in the area. We can go to our directory. Okay. Where is the telephone? Now we are in the directory. And now we can see from the previous running, there are 4 processors. Let's remove them. So we see we don't have any more processors here. Now let's have a look on the batch when we want to submit to the HP system and what the setup it's required. Let's open the batch file. There is the batch file here. It's created for Hierarchical system. When we want to have a batch file, we should look at the partition of the system. For the Hierarchical, we have the IRHPC, which has information about the system. If you go here, learn about the system. Of course, in the lecture of this course, you got familiar with this. About the quick access, of course, all of you have access here about the batch and about the submitting batch. Here, there are some information about the command and S batch to submit the script. And here, the batch script here, how it look like. You can use your email here and to get notification about the submitted job, the partition, number of the nodes, the number of the core per node, and a CPU memory and maximum time for the running. About the partition here, we can see the partition information about the partition. The name here you can use, and it's showing you how many number, the memory. It's all over here. We have different hardware. It's from Intel, from AMD, and the GPUs from NVIDIA. So depend of this information, you can choose your batch, and you can choose your partition and set it on the batch. So here the information is used. This is the email, and this is the partition, number of the node, number of the processor per node, and this is the memory and maximum time 1 hour. Then we need to load the OpenFoam module. Then here in the sequence, firstly we run the block mesh and then set field and then the decompose bar, and then to run this solution in parallel, we need to use this command, MPIX or MPI run. They have a different command here, but we use the MPI execution for processor and the compressible interform. This is something we need to change when we use different cases with different feature. Here, this case from this category, so we use this command and the parallel and the log, and we get the result. we see the batch, how it look like and what setup you need to do. We close this one and we can submit the job and we see how it's going with it. This batch. This works submitted. We can see the job ID. We can, of course, we see its status. And the ID is 18, 46, 41. This is the status of the job. It seems the job completed in 30 seconds. So we can see the result. About the result, we expect to see also here 4, because the setup was for 4. And the solution, we will look at these output and error to see how to. Let's first see the processor is created, which is mean the subdomain is created for 4. Yes, here they have 4 processors, so that means the processors are created. Then we can look at the error file. There is no error. Then we can open the output. This is the output. It's showing us in the sequence what happened. Firstly, the execution for the black mesh. So the mesh are created. Then here the set fields, execution, and then here we decompose R when the 4 processor created. We can see here the 4 processor 0, 1, and 2, and 3. Are created. So here are the example when we're submitting batch file and we see the result. Here we can doing some setup for Power View to connect it to the server, and then we can have a visualization directly on the server and write the command Power View and get the information. The other way is to download the result here, and then you can use the Power View on your local computer and see the visualization. So this is the something that how is going when we are using on the batch file and submitting the job. Let's go back to the solution of the system and see how it's going with that computing. Still it's running. We can go to the section and see how many time is computed. It seems in the half of the way because we have 0.49. It's 0.22, so still there is a time to run to solve the problem in this way. Since it's just to show the difference, we see how it's take time to solve it in this way. Now we can stop this one. And we see when we solve it in the parallel, how it's going with it. Now let's solve it in parallel. When we want to solve it in parallel, we can repeat the solution here for this one. However, let's remove this solution that is take very long time. And now we can make the solution based on the process. Firstly, let's go to look at the system. And open the post bar. The setup on the simple and for one is same the last one we created. Now we can run the simulation for this problem. First, we can start with the mesh creating. Then set fields. Then now here we're using this capability of decompose bar. So the four processes are created. We are not going to look on these visualization now. We continue to solve this problem with the command in parallel, and we see the solution and the result. So let's continue, use the MPI run. Four, one, one. So this is the command we must use when we write in parallel. Here it's meaning we will use MPI run with number of the processor 4 and compressible interform, as I said, is dependent on problem here, which is from this type of problem. So we will run it in parallel on the local system. And we saw the previous one, how long it's taken. Now here we can see the solution of this problem and how long it takes to be solved. Also, we can go to the this CFD direct, and we can see there are some examples from parallel solution, and we can read how we create the command for the parallel application. You can see here about creating the decompose particle here, how it's going, how it look like, and what the difference between the method simple, hierarchical, and a scourge. As you can see, simple decomposition in which the domain is split into piece by direction. Two piece, it's mean when we write here, for example, 2, 1, it means two piece in X and one piece in Y direction. Hierarchical, also it has the same description. And then with this command, the decomposition will happen. When we want to run, as you see here, what we made with the command, when we want to run on the parallel, we're using this sequence of run. There are some setup when we are running on the HP system. It depends that which command we are using. We use MPI execute. If you use MPI run, it will be different setup. And in the end, we can create the reconstruct bar, which collect all information from this subdomain and create the result. Here the solution is running. We can wait for it. And also about the CFD direct, you can look to some example. There are some cases that's how you can run. Also about the solver modules. Here there is some information what the difference between the modules, why we are using this one, or why we, for example, we're using the compressible interform. Here we should have this information. We use it for multi-phase flow. And here you can find the information, different solver. The solution is running due to 4%. We need to wait a little bit to finish this solution. About earlier also, it's good to take a look on the available partition and what the difference. And for example, you can run a simulation with different partition and you see the difference between them, how it's changing the speed up. It's going to be about half the solution. Let's look on the batch file here. We're talking about it. Here also, as you can see from the results from the decompose part, we had four processors, 0, 1, 2, 3. For the visualization, as I said, we can make a same approach we did on the system and visualize them. Also, is it possible to have another visualization? Or, for example, we can have another example on the system with the hierarchical method. If we open another one on the hierarchical here, we can see how the hierarchical also is working. Here we see there are same category. Let's see in the system how it's going with the setup for decomposition. here the decomposition doesn't have any setup, so it seems we can add from the another one. Close it here. The hierarchy one, we can go directly here and we see how it's going with this one. Here we have the decompose part. The hierarchical one. So here we can go back and use the information from the previous one. Mhm. Okay. Yes. Foundation. Okay, here we have the setup for the hierarchical one. Here the setup of the hierarchical and its form. We can make a change. For example, we can make it 6, and we can change here the 3, 2, and 3. Okay, this change for the simple. We need to change it on the hierarchical. Here in the hierarchical, we can change it to be 2, 3, and we'll see the change. So is the hierarchical one. So we need to save it. Let's make the mesh. Here, as you can see, we have 6% now it's created. So based off the setup, we can see how many person is possible to be created. Here the solution by the MPI is finished. So we can take a look about the solution and we see how the solution is created. We need here to create an file for the saving. Then we can use the recon start or so the solution is created here. Now we can make the home to so we can go to the problem here. Change it to alpha water. And when we run the solution, we can see how it looks like. That's the number of the simulation here. It's showing when we have the sphere with 10 bar in the water, and the blue area is the air. This is a simulation showing this explosion of the volume in the water. We can change the time step. We can change the uh, time of the solution in the setup, of course. So here we finish the simulation with this case from the OpenFoam to show how it's working and how the command we are using. And of course, the important thing was the batch file, how we create the batch file to submit the job. I'm finishing this part of the lecture 4.2, and in the end also there is a video. It's showing application of the ANSYS Fluent for CFD simulation. It's good to watch it and see how the application of the CFD is available in many areas. And thank you for your attention. And of course, anytime if you have a question about the lecture or about the assignment, feel free to contact me. Thank you.